This chapter deals with the nature and properties of sound. So all sound ultimately is produced by some kind of a vibrating object. And a good example of that is this tuning fork right here. And this is the prongs of the tuning fork. They're labeled A and B. And when the tuning fork is struck, the prongs vibrate back and forth. So let's look at this diagram on the bottom here. So when prong A moves to the right, it compresses the air that is immediately to its right. And as it moves back to the left toward B here, there is sort of a place where the air molecules can expand in a little bit. So the distance between the air molecules is bigger over here in this area that's called a rarefaction. And they're crunched closer together over here. That's called a compression. And as the prong of the tuning fork vibrates back and forth, back and forth, back and forth, it generates these disturbances in the air that are called compressions and rarefactions. Okay, a couple of things here. Notice that these disturbances are parallel to the direction of travel, which means, as we said before, that sound is a longitudinal wave. And another thing is to understand that sound can travel in other media as well, liquids and solids, and it actually is transmitted more efficiently through those media since the air molecules are closer together, and when the tuning fork or whatever it is vibrating, these disturbances move more efficiently through those media. And I think you probably have seen evidence of that before, maybe listening to a speedboat underwater or listening through one of those telephone cans, things that you may have played around with as a kid. Now, the speed of sound is 330 meters per second plus 0.6 times whatever the Celsius temperature is. So in other words, if the Celsius temperature was 10 degrees, for example, 0.6 times 10 is 6. So the speed of sound would be 330 plus 6, or 336 meters per second. If the Celsius temperature was 20, which is right about room temperature, then 20 times 0.6 is 12, plus 330 is 342. So the important thing to see here is that as the Celsius temperature goes up, so does the speed of sound. Now, sound undergoes reflection as well. And I think everybody is probably familiar with echoes. And when you're in a canyon or even in a room and you yell, for example, you can hear the reflection of the sound off the sides of the canyon or off the sides of a big room or auditorium. So that's an example of reflection. More about that in your textbook. Now, sound also undergoes something that's called refraction. You might not be so familiar with refraction. It's oftentimes associated more with light than air. But basically, it's the bending of the wave when the wave goes into a medium where it's traveling at a different speed. So we noticed up here that as the temperature goes up, the speed of sound increases as well. So, for example, on a warm day, generally the air temperature near the ground is warmer than it is above as you go higher. So what happens in that case when you make a sound, let's say that you're yelling, the sound waves tend to refract or bend in an upward direction because the speed of sound is slower in the areas above as you rise in altitude. On the other hand, in the evening, most of the time, the air temperature is cooler in the ground than it is in the surface. And so in that case, the sound tends to bend more downward. So when it's cooler, the air, a sound tends to travel better in air than it does during the day when it's warmer. And a good example they mention in the book here is if you've ever been on a campfire, maybe around the lake, and there's other people around there, you can often hear their conversations pretty clearly, even though they may be a good distance off. And that's because it's at night when it's cooler, and the waves are tending to bend downward, and so they're staying near the surface of the ground, and so they are more audible. Now, every object has a natural frequency. Good example of this is if you were to take a glass, a good piece of glass, and just hit it maybe with a knife gently, and you'll hear sort of a ring, a sound, and that sound is its natural frequency. Same thing with a tuning fork. A tuning fork has a natural frequency associated with it. Oftentimes that frequency is just stamped right on the tuning fork itself. And anytime you strike the tuning fork, it's going to vibrate with that frequency. Now, an interesting phenomenon is something that's called resonance. And if you have two objects that have the same natural frequency, you can get the second object to vibrate in resonance with the first. A typical physics experiment in the classroom would be if you were to have two tuning forks exactly of the same frequency, you strike one and you can hear the sound, and you stop that by putting your hands around the prongs. You can hear the other one still vibrating because the air, which had the same frequency as the original tuning fork, is causing the second tuning fork to vibrate. Now, one great example of this is you've perhaps heard that it's possible, although it's not very common, but it's possible to shatter crystal with a sound. And that's because what you would have to do that is to match the natural frequency of the crystal with the frequency of your voice. And if you do that, you can get that crystal to start vibrating. If the sound is loud enough, it'll vibrate so drastically that it can actually shatter the crystal. There's another great example of resonance that doesn't really have to do with sound, but it has to do with the same principle of resonance. And this is the Tacoma Narrow Bridge collapse. I'm going to include a video of this in this module. And basically what happened was Tacoma Narrow Bridge was a very long bridge. I think it was built in the 30s or early 40s. And just coincidentally, the natural frequency of the bridge happened to match the natural frequency of the wind gusts that would go through the Tacoma Narrows. And ultimately what happened was it would cause the bridge to start to sway, and finally it came apart. The bridge just collapsed. It's a great video, so be sure to check that out. Okay, sound can also undergo interference. We talked about interference of waves before, constructive and destructive interference. And this is noticeable, for example, in an auditorium. Sometimes there are dead spots in an auditorium where the destructive interference of the sound cancels it out, and so you can't really hear very well at that particular place in the auditorium. The other example of interference with sound is beats. I don't know if you've ever tried to, for example, tune a guitar, and if you tune the guitar with two different strings that are the same frequency and one of them is slightly off, you'll hear a pulsating sound. And the pulsating sound is this beat frequency, where there is constructive interference and then destructive and then constructive, and it happens when the frequencies are not exactly the same, and so the wavelengths are different. So there's constructive interference at one place, and then a little bit further down there's destructive interference. So you hear a beat. You hear that the sound is louder when there's constructive interference and softer when there's destructive. I've also heard students who have played in a band, and perhaps some of you have had the same experience, that when the band is tuning up and somebody's frequency is not quite right, you will hear this beat frequency as all the musicians play their instruments at the same time.